Hello. So this is kind of a part 2 of the previous video I did covering section 3.8 of Reef, where I just kind of want to discuss an example of our force conjugates in statistical mechanics. So let's say we want to derive pressure from volume whenever we are using that particular setup for our force conjugates, right? So we can start off with a statement here, right? That let's say we have the derivative of energy with respect to volume is equal to the partial derivative of energy with respect to our volume. We can rewrite this simply as being that the differential of E is equal to the partial differential of E with respect to volume times some small change in the volume dV, right? So whenever we see dE by itself, or dW, or dQ, or something like that, our first thought should be to go back to first principles and apply the first law. And the first law, in its inexact differential form, doesn't really matter, but this is the way I have it down in my notes, our change in work is equal to our negative change in energy plus our change in heat. Since we're dealing with a mechanical change, really, our change in heat for this scenario can be considered negligible, because if we're looking at pressure, this is the way I reason it. Overall, if we've got our box here, and let's say we have a piston, this very well may not be the case, but this is the way I think of it. So if we're going from here, we just creep it up a little bit more on a piston here to here, we're experiencing that little sliver of a change in volume in some direction R. It doesn't matter what you call it. It can be Z, it can be Y, it can be X. Whenever we're doing that, over that small of a change of a sufficiently dilute gas, and it's not very dense either, then we're not really going to see really any sort of noticeable change in heat. So for the sake of simplicity, we can let dQ go to 0. If I'm incorrect about that assertion, let me know. That's just the way I reasoned it, but that might not be correct or the correct line of reasoning to get to that point, but that's just the way I saw it. So in other words, we're just left that our inexact differential dW is equal to a negative value of dE. But we also know that dW can be written as, PdV. So this is equal to PdV equal to negative dE. So our pressure can be written as a negative differential of our energy with respect to volume, right? So with that in mind, what we can do is that we can substitute this back into what we had initially, right up here. So therefore, dE dV is equal to negative pressure, which is equal to our partial differential of E with respect to our volume, right? So now that we have that established and out of the way, in this sort of differential relationship, where we can move around our differentials and make mathematicians mad all day about, using separation of variables the way we do, we can move on and assess the number of states in our system. That's kind of the part 2 here. So we start off by assessing the differential of the natural logarithm of omega here. I use the natural logarithm of omega because it's normally standard practice, and also it's handy to use a natural logarithm mathematically, because over time a natural logarithm will begin to vary much more slowly. So we can write this using known identities, that the partial differential of our natural logarithm of omega with respect to energy at a constant volume times some incremental change in dE plus another partial differential of our natural logarithm of omega with respect to volume with constant energy is equal to dV, right? So for quasi-static adiabatic processes, which is basically what we have here, we have something that's really not changing by a whole lot very quickly. And our gas is being compressed adiabatically because we're losing some amount of energy here whenever we're doing the work or when the work is done by the system. This term conveniently goes to 0. There's not really any sort of change that we can notice because, once again, it slowly varies, right? So if we set this whole spiel equal to 0, and then we use some of the identities that we uncovered from the previous exploration of this, namely that our partial of the natural logarithm of omega with respect to energy is equal to beta, which if we didn't write this in the previous bit, but that's equal 1 over kT, where K is a Boltzmann constant and T is the absolute temperature. What we can end up doing is that we can re-express this as being as 0 is equal to beta, and then I believe we wrote it in here somewhere, or this is another identity here. This should be equal to dE as well. And in the second term, we don't really bother about changing. Yeah, there's dE there. I'm going crazy sometimes. I've noticed whenever I teach, it might look like I can't do math by myself. And that's partially true. I'm not great at math all the time, and I'm not claiming to be great at math all the time. I just want to make sure that what I'm delivering to you is actually correct, and I'm not, just going crazy. So I'm constantly referencing my reference material in one hand here, and I'm just kind of reading it to you guys. It'd probably be better if I had a script, but oh well. You win some, you lose some. We learned, though, that we can express d of E in terms of pressure, right? So we have this here. If I actually do a different color so we can distinguish the two. Right? So if we have, oh my heavens, dE, dV, there we go, is equal to negative P, then that means that dE, that made it worse. I just need to hang this thing up on something. It's equal to negative P. That is not legible. Negative P dV. Right? Separation of variables. The physicist's best tool. We can substitute this value down here. So we get beta times negative pressure dV plus the natural logarithm, the derivative of the natural logarithm with respect to volume at constant energy dV, right? So we have that, and we can just basically move terms around because this is equal to 0. We want the expression to be in terms, we want the expression to be pressure in terms of other stuff. So what we get is beta pressure change in volume is equal to the partial of the natural logarithm of omega dV. I'm going to erase that because that looks atrocious. There we go, with respect to E. dV. We have a dV on both sides, so they can go away. So what we're left with is that we have beta times pressure is equal to the natural the derivative of the natural logarithm of the number of states with respect to volume. Notably, at some constant temperature, or not constant temperature, constant energy E. And that would be a generally, I would say, pretty decent exploration of how to do a problem like this, namely finding the dependence of pressure on a variable or parameter like volume.